I've been enjoying solving daily Sudoku puzzles with an app on my phone. Until recently, that is, because the app that I've used has started to introduce ads that interrupt me in the middle of my games. Now, I don't have a huge problem with ads in free apps. I'll deal with the banner ads as I know it helps developers generate revenue, and I'll even tolerate the more annoying full video ads that happen before and after completing Sudoku puzzle. But I draw the line at interrupting my user experience to view an ad that I can't avoid and have no way of knowing when it'll happen. Basically, my frustration with these ads has reached a breaking point. I mean, it's just Sudoku. Heck, I could make this. And so I have. So come along with me as I show you how I went about making my own daily Sudoku puzzle app to replace this annoying ad-riddled app I currently use. Now, this will be a two-part video series broken up into the first part that's focusing on the actual puzzle generation, and the second video showing the actual app UI creation and gameplay. This was going to be one video, but after completing the puzzle generation, I wanted to make two slightly normal length videos instead of one really long video. But let me know what you guys think in the comments. Now, before I do any programming, I need to come up with a plan of action. Originally, I thought this would be a great way to relearn Kotlin and Android app development, but that would lock me into an Android-only app. Also, Android development can honestly be a pain, and for a project that needs no special Android features, well, my desire to make this an Android app quickly faded. I wanted to make this cross-platform in terms of iOS, Android, and the web, but platforms like Flutter and React Native just never interested me. Another option that has been gaining traction though recently is progressive web apps, or PWAs. A very short TLDR is a PWA is basically a web page that can be installed or saved to a device, and is also able to access certain device features like storage or even the gyroscope through APIs. Now, I'm not sure I will need any of those fancy APIs, but the key part is that this is just a regular web page with a few extra bits of code to make this installable on an Android or iOS device, giving me my cross-platform. Bonus points, this also allows the web app to work offline. So PWA it is, and my plan is to write the actual web app using Solid.js, but I'll get into more of that in the next video. For today, I'll be working on the backend, the actual Sudoku puzzle generation code that will be allowing me to generate my daily puzzles. I'll be using Go for this part mainly because I'm still wanting to get better at it and use it more often. I've really enjoyed my time working with it so far. Anyways, the reason why I'm making this separate from my PWA code is because I want everyone's daily puzzle to be the same, and thus needs a central backend. No, this is not the only way to do this, and I very well could have gone without a backend, but this is just the way I chose to do this project. I'm going to say this now though, and I'm assuming you, the viewer, knows the basics of what Sudoku is, so I won't be explaining any of the game rules. If you don't know how Sudoku works, feel free to use this wonderful platform we call YouTube to find a video explaining it, and then come back to this one. Anyways, enough talk, let's write some code. The first step to all this is to generate a valid Sudoku board. This ended up being a bit harder than I thought it was going to be. My first attempt was to fill in the board row by row, choosing a cell's value from a list of possible options. When the value is chosen, update that cell to the given value, and then update all the other cell's options to reflect that new cell's value. And then check for the cells with only one possible option left, and fill those spots in before continuing on with filling in the next cell in the row. This did not work at all, as tons of cells were left blank, represented by a 0 here, as they just did not have any valid options left when the code got to them. Simply put, I was just too naive with this attempt, and the rules around a valid Sudoku board just made it a bit more difficult than I was expecting. And yes, I know I could have looked up a real algorithm for all this, but I wanted to give myself a shot at figuring it out on my own first. Okay, no worries though, instead of going row by row, let's go box by box and avoid the issues from above with cells running out of possible options. Let's generate boxes 2, 4, 5, 6, and 8, forming a big plus. In theory, this should provide the best overall generation with as little conflicts, right? Unfortunately, it also erred, but interestingly, only when boxes 4 and 6 were included. The vertical 2, 5, and 8 worked without a problem. After some debugging, I found simply flipping the row and column iterators resolved this error with the whole plus was generated. I guess it was something to do with the order in which values are chosen and assigned. I likely just got lucky though, as adding a loop to generate more boards errored out with the same problems as the first attempt. I think this trick just doesn't really give me anywhere new, so let's go back to my original attempt, but this time instead of going row by row, let's simply go box by box and try to create an improved single cell option locator. That is what I told myself when I started my third attempt at this, but I quickly realized it didn't matter what I did to the single option cell locator logic, it just wouldn't be enough to be able to guarantee all cells would get a valid number. The problem is that I need to be able to backtrack on my choices when I reach a cell that has no options. so that I can pick new numbers that will lead to this cell having a valid option when I get back to it. So while this third attempt may have been a complete flop, I think I've actually have a new plan of attack and utilizing recursion to generate my boards. I have high hopes that this new plan of attack will work, but I'm not sure it'll be fast enough to be practical. Only one way to find out though, so for my fourth attempt at generating a valid Sudoku board, I decided to go back to going cell by cell and picking a random number from the cell's available options. I then place that number in the cell and update all other cells options based upon the newly placed number. I then proceed to the next cell and check that cell's available options. If the cell has no valid options to pick from, I return back false on this recursive method, signifying an invalid board. That triggers a recursion to move back up the stack, and cells will undo their choices and attempt to pick new values from the remaining options in their cell. If no other options are available for the cell, we continue on back up the recursion stack, and once we reach a cell with another attempt to pick, we then resume the recursion there. The recursion will finally end when cell 80 has gotten a value assigned to it, at which point this method returns true, causing the entire recursion stack to return true and thus leaving me with a valid Sudoku board. Best of all though is that this is actually fast enough at generating boards, it seems pretty instantaneous, so we finally have a winning method. Now the Sudoku board's generated, it's time to ungenerate it a bit and then present it to the player to solve. The tough part here will be making the boards both solvable without having to resort to random guesses, and also determining how difficult it is to solve. This part I had zero ideas on, and while I have written a Sudoku solver before, assigning a difficulty to that is a whole other step. So I resorted to a quick Google search and ended up coming across a website, then articles where they outline how they assign their difficulties. I won't even begin to try to explain the techniques towards the bottom of this list, but I can use this as a guideline to write my own solver that would be able to solve puzzles and assign a difficulty to them. Essentially, I would just follow the technique steps, and after summing up the total score, use the range in each ratings to assign the score to a difficulty. To actually ungenerate the board, I'm going to progressively remove numbers randomly from the board and test that the board is still solvable. The algorithm will keep attempting to remove numbers until it reaches a value within the desired difficulty range or runs out of cells to remove, at which point it will generate a new board and then go through this process again. The first step to all this though is writing the solver. I don't need to implement all the strategies listed right away, only enough to be able to make puzzles in the lower difficulties. To start, while the puzzle is not solved, go down the list of solve techniques in order of difficulty and try each one until one is able to fill in a space. Then log the move and the process repeats. If no techniques are able to make a move, set the difficulty to -1 to signify this board is not solvable without guessing, and then break out of the loop. Every loop iteration we will also regenerate the cell's options, just to keep it simple, and also do a sanity check that there are no cells with no valid options. I implemented the single candidate technique and tested it with 1 and 2 numbers removed from a board, and they both worked flawlessly. Honestly, this Sudoku of the Day slate was a fantastic resource. Its step-by-step solutions made it easy to debug my code, and their puzzles list the techniques required to solve them, which provided an easy test case when I added a new technique. Probably would have struggled a lot more without the site to help me. Anyways, first 2 techniques were easy to implement, and we can now solve and, in theory, make easy puzzles. Before I try and make a puzzle though, I wanted to try and implement some more techniques. Only problem with the next techniques is that they don't actually add any numbers to the board, they only remove options from the cells. Because of this, I need to rewrite my logic as I can no longer generate all my options every loop because that would just wipe out any progress this step makes. At this point, I also decided to create a common board struct that both the generator and solver can utilize so that some of the more common logic with generating options and placing numbers can be condensed. With that out of the way, generating options was moved to a one-time operation at the start of the solve, and techniques now called place number method on the board, which will automatically update all cells options. With these changes now made, I can add the logic for the candidate lines technique, and only if this technique removes an option from a cell will it return true. For the next 2 techniques though, I ended up deviating from the website. They list double pairs and multiple lines as the next techniques, but after looking into how they work, I actually combined them into one based upon how I actually solved the Sudoku puzzle. Instead of looking for these pairs or groupings across multiple boxes that these 2 techniques do, I actually look for the opposite. I look for places where a row or column in a box has options that don't exist in other cells for that row or column in the other 2 boxes. If these don't exist, we know that this option must be valuing one of the cells in this box's row or column, and thus the other 6 cells cannot have this option, so we can remove them. I ended up basically copying the logic from candidate lines, but instead of looking in the same box first, it looks across the same row or column to find the candidates. It then finds one, attempts to remove the candidate from the rest of the boxes, and like the candidate lines, will only return true if an option was successfully removed. Also, because I condensed these two techniques into one, my puzzles will also have a slightly different difficulty score from the website. Just something to keep in mind. Next up is the 2 or 4 advanced techniques, with the first 2 being the naked doubles and triples. While these are 2 separate checks and difficulty scores, they work very similarly and have the same function. I go column by column or row by row and convert each cell's options to a string. I then add that to a map with the key being the said string and the value being the total occurrences of said string in the row or column via a slice that holds the cell's location of the occurrences. I then loop through the map and find the entries where the length of the key matches the length of what we're looking for, 2 for pairs and 3 for triples, and then check that the value equals the number of occurrences and thus also matches that length. If an entry does match this criteria, I attempt to remove each of the candidates from the other cells in the row or column. Just like the techniques before this, if a candidate successfully removes another cell's options, we return true to mark that this technique has worked. The other 2 techniques that I tried to implement before I actually started generating some boards were the hidden pairs and triples. Unfortunately, my solutions for the previous techniques did not help me here. Maybe there is a solution that works for all 4, but I didn't currently know it. Because of that, I decided to try a different approach for these 2 and ultimately just worked on a solution for the hidden pairs and left hidden triples for the future. To solve this, I go through all cells in the given row, column, or box and log how many times each number has appeared as an option. In order for a hidden pair to occur, the number can only appear twice in all cells as an option. So I loop through and make a list of all numbers with only 2 option appearances. From that list, generate all the combinations of the 2 number pairs. For each combination, check how many times that combination number shows up in each of the cells in the row, column, or box. If it does not show up twice, this combo cannot be a hidden pair. If it does show up twice, we have a hidden pair. Lastly, go through all the cells in our row, column, or box to find the cells with this combination and remove all other numbers. If other options are removed, again, return that this technique has worked. And with that, we are now solving some pretty difficult puzzles. I will note that even though my difficulty scores no longer are the same as the Sudoku of the day due to a few factors, they are generally pretty close. With all that said, time to move on to actually generating the puzzles. Basic premise for my generator is that I choose a random target difficulty, then remove numbers until the difficulty range is reached. Overall, it wasn't too hard to implement. I did follow Sudoku of the day and I picked a random cell from the available cells, then also picked the rotational counterpart to the cell with this formula. I then remove both from the available cells list and also set their board values to 0. Again, 0 signifying the cell has no set value. I then run this board through the solver. If the difficulty is -1, meaning it can't be solved or is greater than the expected range max, I reset the cell's values but leave the cells out of the available list so that they don't get picked again. If no more cells are left to pick, I generate a new board and start this whole process again. And this worked! Sorta. It struggled to get puzzles with a high enough difficulty score to reach the minimum values for anything but easy. But the solver is clearly capable of solving puzzles in all of these ranges. Turns out I just forgot to recopy the board to the temp board variable I was using. With that fix made, our generator worked like a charm. It occasionally takes a few tries, but for a first attempt at this without really trying to optimize anything, I'd say it's pretty darn good. In the end, puzzles of either easy, medium, or hard difficulties can be generated from this code, and it's all done with this one nice concise main method. Hard puzzles occasionally take a second, but in theory as I implement more of the harder techniques, this should actually get better. And with that, part 1 of this project is complete. For part 2, I will actually create our PWA and then integrate this generator into it. Now, I hear what you're saying, and yes, this is all written in Go, and yes, PWAs, as the name suggests, are web apps that should work offline. So how am I going to make all of what I just created work offline when the point of this code was to be the start of a Go backend or a REST API to generate a daily puzzle? To that I say I may have a trick up my sleeve involving WebAssembly, but you'll just have to come back for the next video to see how I do it, and so you don't miss that video, consider subscribing. Let me know how you like me splitting up this larger technical project into multiple discrete parts, and also let me know if you have any comments on my Go code. I am not the most knowledgeable with Go, and I've only written code with it a handful of times, so this is far from being great Go code. Links to everything will be in the description below, including the source code, so feel free to go check it out there. On that note though, hopefully you guys enjoyed. Thanks for watching, I'll see you guys next time. Peace out.